Hello everybody. Today we don't do volume or surface or anything, but we do integrate the vector field. Now first of all, what is a vector field? Okay, vector field is a new way to organize the physics system. What I mean is, suppose you have the water fountain here and the water flow out, okay? Then you want to know how much water is flowing. You put the monitor here and measure each place, okay? So in order to have this kind of system, monitor and analyze, what you need to know is, say, velocity at this point and maybe height, right? If it's in the mountain, okay? So this is what you need in the steady state. Means this flowing pattern doesn't change by time. There's no time here. You can put the time, then that's not for transient property. It's steady state. We need to know this. So instead of using Newton's original equation, there's a mass flowing out every direction, and make a differential the Newton's equation for each mass. That kind of analysis is it's going to be out of control in this kind of system. This is a fluid dynamic. And mechanical engineers go through this. When the is a steady state, we don't need Newton's equation. Some kind of mass ma, and this is a sorry, this is the ma equals flowing force kind of analysis. This is almost impossible to use. So we define this kind of field parameters, which called the field theory. Okay, so field theory, you have x, y, z, and important parameter like a velocity is all over. This water velocity here, 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 everywhere, and that's what all we need to know in order to know what's going on. So in order to analyze this system, what you need is the field information. And using this field information, there are a few things you can do, and one of them is called Gauss law. And this Gauss law, the same concept apply to electrical engineering, which is, suppose you have a charge, electric charge, like electron, and say this is the density. Every space have some charge, and total this much charge. So what we say is the flux is coming out from each charge. The flux is called electrical flux, D, and you know D is related to electric field, right? And permittivity is relative permittivity and permittivity for vacuum. So you learn this in physics. Electrical engineer has to go through this. So same thing, if instead of water the flux come out, and source of the flux is charge Q, positive, right? And negative is like flux is going to be sucked into, which is like a sink in the fluid dynamic, right? So the same way, D is also defined everywhere. You take this point, how much d is going. D is like a vector, just like a velocity vector, right? and the vector is all over in the field, vector field. Okay, so using this, what can we say? Okay, suppose we take this enclosed area, right? And this enclosed area, we check D on every point, and D may be crossing this way. This is the boundary, okay? Or boundary crossing this way means D is coming into the enclosed area, or go straight up. Okay, so our objective here is to calculate total amount of D coming out of this enclosed area to the outside. So how we do that? We take this element, surface element, which is a ds, and this is a vector, means the unit vector pointing outside, right angle. Okay, so this can be dx dy, the area, or ds, area ds, but pointing outside. And if you use this ds, the amount flowing out is not exactly d, it's going to be ds, because if kind of angled flow, the actual flow is this right 90 degrees direction. The remaining is going along. For example, if you have this boundary, if flow is like this, it's not going in or out. This is the ds. The d is flowing out or flowing in to the enclosed area. You do ds, d is 0. So 90 degree, the vector, inner vector ds is 0 if 90 degree, right? So only the element component go along with this ds, which is pointing 90 degree outside of this surface element, is going to be the actual quantity. So what we do is, this enclosed area is A enclosed, this means enclosed, okay? Then D dot ds, and this is going to be the total amount of D coming out from this enclosed area, okay? And also you can have another integration, is volume integration of charge density volume, and this is the A. The A is not surface, A is volume, this A is surface, okay? And what the Gauss law said is they will be equal. So what Gauss law said is, whatever the source of D, Q generate D, right? So Q generate the D, this charge density, you integrate, volume integrate this entire amount of Q. That will be same as total flux coming out from this enclosed boundary, which is D in multiplication ds. Okay, so this is the Gauss law. Okay, Now, Gauss law we modify a little bit. The ds is like dy dz I plus dz dx j plus dx dy z. Okay, for example, x y z, right? And dx dy and vector, unit vector z. So you have a three different direction, and d is going to be dxi plus dy j plus dz k. Sorry, this is k, right? Yeah, in the convention. So inner product is d ds is going to be surface integral dx dy dz plus dy dz dx plus dz dx dy. Okay, so this one, the surface integral, if we know dx we can use this to calculate this. So what you do is, instead of this is surface enclosed plus this x direction, we integrate dx then dx dy dz, and so you do same thing, integrate along y a dy dy dx dy dz and plus dz a dz dx dy dz. So if you know dx dy dz is a volume dv, right? So instead of integrating with x and yz or y and xd, just change the order, then this whole thing is going to be, say, dx plus dy dz dx dv, and this time enclosed volume integral. Same thing as volume integral. So this is gonna be volume integral. Volume, you can put three of them. Okay, so q dv. So Gauss law said this one is going to be d, right? Or you can say divergent is same as q, the charge, electric charge density. Well, you cannot say a something and b something because this integral is is equal. Is this correct? Not really, right? Okay, so you cannot say this one is this, but you can say it in this case. The reason is Gauss law, this Gauss law is correct for any A. For example, you go back and you use a little bit different boundary, the same relationship, or smaller boundary, same relationship, or take the half, same relationship. So when this integral equals this integral for any boundary A, then you can say this equals this. Okay? The precise proof, mathematical proof, you have to go through a little bit more convincing argument, but you can tell, right? If boundary, any boundary, it's same, so it should be exactly the same thing. Okay? And that's why Gauss' law is often written this way, or divergent electrical field is epsilon, right? Permittivity, because D is epsilon E. Okay, so here the Q, in this Q is charge density. It's not total amount of charge, okay? It's a charge density. Okay? Total amount of charge is this one. This is the total amount of charge. So suppose you have n electron, and Ne is total amount of some kind of Q is Ne. Let's see, you have a bunch of electron is Q, and you have a Q here, and you take some boundary here. Any boundary is should be same. So this Gauss law indicate here's a Q, which is Q is distributed inside this volume. Here's a 0. Q is 0, and Q is 0. So what does it say is D come out, and is in this area the D is 0? Not really. Differentiation of D is 0, so D can be constant. So D is constant. If there's no Q, D doesn't change, and this constant D you can integrate around. Okay, then you can get total same quantity Q. You can get the Q out by this. Okay, now why Gauss claim is correct, that's the subject for the next video. But today we go through integral form of Gauss law, which is enclosed surface integral. This is area, so surface integral is going to be same as the same enclosed volume integral. So integration form of Gauss theory. Okay, now derivative form is going to be Q. Oh, I'm sorry, we don't need this here. The flux, you integrate all the flux on the surface of enclosed area is going to be same as this. It's okay. Don't make a mistake. You don't need divergent. This is same as so this is so often you see as a Gauss law. Okay, so this derivative form. Okay, so from integral form to derivative form, you can go only when this Gauss law is correct for any enclosed surface, right? Yeah. So any enclosed surface, if integral form is correct for any integral surface, then derivative form is correct. And if derivative form is correct, you take an integral on both sides. Okay, the volume integral and the volume integral change to surface integral, then you get this one. Okay, now important thing is, what can you tell from this one is the existence of Q change D. This is derivative, right? So D change by Q. If no Q, D is constant in the space. It doesn't change because derivative is 0. Okay? And if there is a Q, if positive charge, then D increase. If negative charge, the D decrease. Only existence of charge is going to change D. Okay? So if you have a distribution of Q in a space, you can tell the D increase, and if suddenly Q disappear, then D increase up to here, then from here D stay constant all the way. Okay, you need this kind of insight in order to solve the physics problem using Gauss law. Okay, so if today's video is good, please subscribe, and any question you can write. I try to answer those questions. Okay, so see you next time.